Welcome to the Sleepy Scientist. I am glad you are here, no matter if you are drifting off, winding down, or just looking for a quiet friend to keep you company. This is the right place for you. Before we start, I would like to know where in the world you are listening from tonight. Are you wrapped up in bed or maybe curled in a quiet spot on the couch? Wherever you are, I hope you are comfortable, relaxed, and ready to explore something quietly amazing. And if you find these calm trips through science soothing or interesting or even just oddly specific, please like this video and subscribe to the channel. It helps more people who like calm stories find this place. And for those who already subscribed, thank you. You are the center holding this whole sleepy galaxy together. I will try not to make this too exciting, but if you do stay awake, at least you might learn something about the universe before you drift off. Tonight we are following a question so big, so quiet, and so strange that it feels like something from a dream. Can two black holes become one? They start far apart, separated by light years, but gravity has a plan. One day they will spiral toward each other, not with rage, but with quiet certainty. No sound, no light, just the slow steady curve of space and time pulling them closer. Black holes are the most mysterious things in the universe. They defy our instincts, push the limits of physics, and seem to live on the edge of what we can know. They are not really holes, but places where gravity is so strong that even light cannot escape. Yet they are not evil or monstrous. They just exist, still, powerful, and even in their silence, black holes have a story written not in words or light, but in gravity, slowly unfolding across the vast universe. In this video we will follow the story of two black holes. We will see how they form, how they move through space, and how under the right conditions, they can find each other slowly, at first, like noticing each other across an impossible distance, then with growing urgency as gravity pulls them into a spiral, a dance that could last millions or even billions of years, until they finally merge into one. This is not science fiction, it is science. And not only has it happened many times, but we have found a way to hear it, with the help of gravitational wave detectors. Scientists have listened to the last moments of black holes colliding, these ripples in space and time, so tiny they are smaller than a proton, carry stories of great power, quiet collisions, and the invisible forces that shape the universe. But before we reach that, we will slow down, we will take our time, because this story is not just about the science of collision, it is about the poetry of gravity, the way it brings things together, the way it bends the rules of space and time, the way two dead stars, long forgotten by the living, can create something new by falling into each other. We will look at how black holes form, how they change the space around them, and how they shape entire galaxies. We will drift through the early universe, where black holes may have planted the seeds for everything we see today. And we will see what happens when two of these objects meet, what they leave behind, and what we might learn from the echoes of their union. You do not need to remember equations. You do not need to stay awake for every moment. Just let the ideas float by like stardust. There will be gravity to catch them, so let's start. Let's follow two black holes on a trip through space and time, a trip billions of years in the making. What happens when they meet? What do they become, and how does the universe remember it? In the quiet dark of the cosmos, there are places where the rules change, where time slows, space bends, and the normal becomes impossible. These places are not made of matter the way we think of it. They are not solid, not gas, not even empty. They are black holes. Places where gravity has total control, so much that nothing, not even light, can get out. To know what a black hole is, we have to see how stars live and die. Most stars like our sun shine for billions of years, powered by nuclear fusion that turns hydrogen into helium deep in their cores. This fusion pushes outward, balancing the inward pull of gravity. It is a cosmic standoff that defines a star's life. But one day the fuel runs out, and when it does, gravity wins. For small and medium stars the end is calm. They shed their outer layers and fade into white dwarfs, dense glowing leftovers that cool slowly. But for huge stars more than 20 times the mass of the Sun, the ending is far more dramatic. When these giants run out of fuel, they collapse under their own weight in an instant, causing a supernova, one of the most powerful blasts in the universe. What remains depends on how massive the core is. Sometimes it becomes a neutron star, a city-sized object so dense that a teaspoon of it would weigh billions of tons. But if the core is heavy enough, not even neutron pressure can stop the collapse. It goes past atoms, past protons, into a point of no return, and that is when a black hole is born. But what is a black hole really? Is it a thing, a place, a hole? In truth, it is more like a region of space where gravity has become absolute. At its edge lies the event horizon. This is not a wall or a surface you can touch. It is the distance from the center where escape is no longer possible. Cross that line and no matter how fast you move, even at the speed of light, you cannot get out. The name black hole fits, not because it sucks things like a vacuum, but because once something crosses the event horizon, it can no longer send any signal back, no light, no sound, nothing. It disappears from the visible universe, leaving only its gravitational mark. In this way, black holes are like cosmic secrets, hidden pages in the book of the universe, closed and unreadable. At the center, if the math is right, is the singularity, a point where the known laws of physics fail, where density becomes infinite and time may stop working in any normal way. It is not that we know what happens there, we do not. It is that our theories cannot describe it. General relativity stops working and quantum mechanics has no complete answer yet. The singularity is not a place we can visit. It is more like a question mark than an ending. From outside, black holes do not look dramatic. They are perfectly round, completely dark, and have no features, but their pull is huge. Close enough and even light bends around them. This bending, called gravitational lensing, lets astronomers find black holes indirectly by watching how they change the light of stars and galaxies behind them. Some black holes are small, just a few times the mass of the Sun, called stellar mass black holes, likely formed in large numbers across the universe. Others are supermassive, millions or billions of times the mass of the Sun, found at the centers of galaxies including our Milky Way. In between, we are still searching for mid-size black holes, the missing link in our understanding, but whatever the size, the rule is the same. Once you cross the event horizon, you are no longer part of the visible universe. You become part of something silent and final. There is a strange beauty in that. Black holes are not storms or explosions. They are the frozen leftovers of great energy. They do not make noise or rage. They just bend space so deeply that the rest of the universe falls inward. Slowly, even now scientists are still learning how they act. New telescopes like the Event Horizon Telescope have begun to take images of the shadows black holes cast. Instruments like LIGO and Virgo have detected the whispers of black holes colliding. Yet with all this progress, black holes remain deeply mysterious, part reality, part puzzle. They are the natural result of gravity taken to its extreme. They are bound to exist in a universe where stars die and time bends, and they remind us that even the most basic laws, like how things fall or how light moves, can break down in the right conditions. To understand black holes is to understand the extremes of nature. They are not exceptions to the rules. They are the rules pushed to breaking, and though they may seem far away, they shape galaxies, change the flow of time, and leave echoes across space. In their silence, they speak of something deeper, something both frightening and beautiful, the universe folding in on itself. Gravity is something we live with every day. It is the quiet reason our feet stay on the ground, why apples fall from trees, and why the moon never drifts away. It feels normal, gentle, steady, but in the far corners of the universe, gravity turns strange, so strong and warped that it stops making sense in the way we are used to. Nowhere is this more true than with black holes, where gravity does not just pull, it changes reality. To see how unusual black holes are, it helps to understand gravity the way we first learned it. For centuries we saw it through Isaac Newton's idea. He thought gravity was a force, an invisible thread pulling objects toward each other. According to Newton, everything with mass pulls on everything else. The more mass and the closer it is, the stronger the pull, simple and elegant, and for most things, this works perfectly. It explains why Earth holds us here, why the Moon orbits Earth, and why planets go around the Sun. But Newton's view treated space as a fixed stage, a flat floor where objects move and tug on each other. In the early 1900s, Albert Einstein brought a new idea that changed everything. He said gravity is not really a force, it is the bending of space and time. Mass tells space how to curve, and space tells objects how to move. Imagine a trampoline pulled tight. Put a bowling ball in the center and the fabric dips. Roll a marble near it and the marble curves inward. Not because something is pulling it, but because the surface is bent. This is general relativity. Gravity is geometry. The more massive something is, the deeper the curve it makes in space and time. Planets make small dips, stars make bigger ones, but black holes punch straight through. What makes black holes so unique is not just their mass, but how small they are for that mass. A black hole is not huge in size. One with the mass of our Sun would only be about 6 kilometers across. The size of a city, all that mass crushed so tightly that the curve is too steep for anything to escape. This connects to the idea of escape velocity, the speed you need to break free from an object's gravity. Earth's escape speed is about 11 kilometers per second, the Sun's is over 600 kilometers per second, but at a black hole's event horizon, the escape speed is the speed of light, and since nothing moves faster than light, nothing can get out. But the real mind-bending part is what is at the bottom. If you follow the math inward past the horizon, past the warped layers, you reach the singularity, a point of infinite density. Infinite is a word science avoids. It is like a flag that says we do not know what is really there. It means all the mass is in a single point with no volume, breaking every rule we have. Our physics cannot handle this. Relativity and quantum mechanics both fail here. We need a theory of quantum gravity to explain it, but from the outside, you would never know. Black holes are silent and round, not storms or chaos. Their presence shows in how they affect nearby things. Stars move too fast, light bends oddly, time slows, and here is something stranger. Gravity near a black hole pulls on time itself. In stronger gravity, time moves slower. Near the event horizon, clocks tick much slower than normal. From far away, anything falling toward a black hole seems to slow down and freeze just above the edge. But for the falling object, it crosses the horizon and keeps going. Time, space, light, and motion all get twisted in this gravity. This bending is what makes black holes unlike anything else. They are not just heavy, they are concentrated in a way that reshapes reality itself. Their pull is felt beyond the event horizon. They can hold stars in orbit, bend light paths, and even shape galaxies. Yet from far away, their gravity works like any other object of the same mass. If the Sun were replaced by a black hole of the same mass, Earth's orbit would be the same, just colder. Black hole gravity is not stronger but deeper, a plunge. Instead of a pull, a silence hiding the loudest truths in the universe. In the end, they show us that gravity is the shape of reality, and sometimes that shape folds inward and disappears from view, leaving only the memory of what was there. Every black hole starts as a star, but not just any star. Its story begins in a cloud of dust and gas called a nebula. These clouds float quietly in the galaxy until something disturbs them. Maybe a shock wave from a nearby supernova. This ripple makes the gas start to collapse. Gravity pulls the atoms closer, clumping hydrogen into tighter spots. As the gas falls inward, pressure builds in the center. It gets so hot and dense that hydrogen atoms fuse into helium, releasing huge amounts of energy. A new star is born, burning steadily and shining outward. This fusion pushes outward just enough to balance gravity pulling inward, creating a fragile balance that can last millions or billions of years. Big stars burn hotter and brighter, living shorter lives. A star like our Sun can live for more than 10 billion years, but a star 20 or 30 times bigger may only last a few million years. Inside, they fuse heavier and heavier elements, hydrogen to helium, helium to carbon, carbon to oxygen, building layers like an onion, until they make iron. But fusing iron does not make energy, it takes energy instead. When the core turns to iron, fusion stops holding up the star, gravity wins instantly, the core collapses in seconds, atoms crush, protons and electrons merge into neutrons, the outer layers bounce off the core, causing a huge explosion called a supernova. For a short time, the star can shine brighter than whole galaxies. The blast sends light racing across space, telling the universe it has died. What remains depends on the core's mass. If it is 1.5 to 3 times the mass of the Sun, it becomes a neutron star, a dense ball no wider than a city. In a neutron star, gravity crushes atoms but not enough to make a black hole. A teaspoon of it would weigh billions of tons. But if the core is too heavy, even neutron pressure cannot stop the collapse. Gravity keeps going, compressing it beyond all known limits into a point with infinite density, a singularity, and with it comes an event horizon, the invisible edge of no return. From the outside, the change is silent, no flash, no ripple, the matter just vanishes into darkness. What was once a star is now only mass, spin, and charge, no surface, no features, just gravity. Only the most massive stars end this way. Smaller ones will never reach it. They will live long, shed their outer layers, and leave behind white dwarfs, dense but stable, glowing slowly. But the giant stars burn fast and die young, their lives measured in millions of years. When they die, they also create heavy elements like gold and platinum in their violent ends. These elements drift through space, become part of new clouds, and help form planets, people, and everything we know. In this way, the death of massive stars is both an end and a beginning. Without it, there would be no carbon for life, no iron for blood, no silicon for bones. So black holes are not born alone. They are part of the grand cycle of matter. They are the final act of certain stars, written not in fire but in collapse. They happen when mass is crushed beyond the limits of light, when the fire goes out and gravity whispers, "Come closer." It is tempting to think they are rare, but there may be thousands in our galaxy. Each one was once a star, bright and alive, maybe with planets, Now they are invisible markers of gravity's power. They're pull-shaping stars nearby, bending light, and moving unseen through the galaxy. They are not gone, just changed. Reminders that even the brightest stars can fall, and in doing so make something stranger than fiction. Imagine space not as empty but as something soft that can bend, stretch, and ripple. Picture a huge rubber sheet pulled tight. Put a bowling ball in the middle and the sheet sags. Roll a marble and its path curves toward the dip, not because it is pulled by a string but because the surface is bent. This is how Einstein described gravity in general relativity. Space and time are woven together into a fabric called spacetime. This fabric bends when mass and energy are present. The more massive something is, the deeper the bend. Earth makes a small dent, the Sun a deeper one. But a black hole does not just make a dent, it punches right through. This bending is what makes gravity work. Things are not pulled by invisible ropes, they are moving along curves in spacetime. When you throw a ball, it moves straight through space that is itself curved. The path bends because the space is bent. Near a black hole, this curve is extreme and time itself changes, one of relativity's strangest ideas is time dilation. Time moves at different speeds depending on how close you are to a massive object. Near a black hole, this effect becomes huge. Clocks tick slower, seconds stretch, minutes take longer. If you stayed near the event horizon, you might feel only a few hours pass. But far away, years could have gone by. This is real and measured. We have seen it with satellites and atomic clocks. GPS even has to adjust for it. Near a black hole it is much stronger, if you could survive it and come back. The universe would be older while you barely aged. Time and space are not separate fixed things. They are part of the same bendable fabric, and gravity bends them both. Light also follows these curves. When it passes a massive object, it bends. This is called gravitational lensing. It lets us see black holes indirectly. If a star is behind a black hole, its light bends around the gravity, creating arcs, rings, or multiple images. These patterns show us how much mass is there. Even if we cannot see it, sometimes it makes a perfect circle called an Einstein ring, where light wraps completely around the invisible mass. Near a black hole, spacetime bends so much that light can orbit it in a region called the photon sphere. Here, photons can circle forever, unless pushed inward or outward. From far away, a black hole's shadow is surrounded by glowing light from matter around it. This is what the Event Horizon Telescope saw in 2019. Not the hole itself, but the shadow it leaves in light. It was a picture of space twisted on itself. Near a black hole, directions lose meaning. Down is toward the center. Time stretches strangely, and space curves so much that you could move in what feels like a straight line but end up back where you started. Light bends. Time slows, and the rules feel more like a dream than reality. But these effects are not just theory, they have been confirmed by observing starlight bending in an eclipse. the red shift of light escaping massive galaxies, and the fast movement of stars near the Milky Way center, all prove that gravity is the shape of space. Black holes take that shape to its limit. They are not just massive, they are events in spacetime where the curve becomes so deep it seals itself. The closer you get, the stranger it gets. Light curves like a river. Seconds can turn into centuries. Everything stretches and twists until familiar rules fail. Yet physics still works. It bends but does not break. The same rules that make an apple fall also guide galaxies around black holes. The difference is scale. Looking at black holes is seeing the edge of what space and time can do. They show us that the universe is not rigid but flowing, curving, and warping with mystery. In their silence, they remind us that gravity is not a shout but a whisper, gently reshaping reality just out of sight. In the deep quiet of space, even black holes can find partners, though it might take millions or billions of years. Gravity has a way of bringing them together, and it happens slowly, not suddenly. Imagine two black holes drifting through a galaxy, invisible but gently tugging on nearby stars and gas. Maybe they formed separately from different massive stars in a dense star cluster. Or maybe they were born together in the same collapsing cloud, like siblings meant to meet again, if they pass close enough. Their huge gravity fields start to interact. At first, they might orbit loosely, far apart, like shy dancers across a giant floor. There is no friction in space, no ropes or magnets pulling them, just their own mutual pull. Over time, their orbit gets tighter, not because something pushes them, but because they are losing energy. Each time they circle, they send out tiny ripples in space called gravitational waves. These are not sound or light, they are stretches and squeezes in spacetime itself, moving outward in all directions like ripples on water. They carry energy away, making the black holes move closer. The process is called an spiral and can last for ages. In the beginning, the waves are too faint to notice, but the process never stops. Slowly they spiral in, round after round like clockwork. As they get closer, they move faster, until they are orbiting at a big fraction of light speed. Picture two invisible objects, each as heavy as several suns, circling each other dozens of times per second. The energy in those last moments is huge. For a brief instant before merging, they can release more power in gravitational waves than all the stars in the universe give off in light. Yet this burst is silent. Unless you are a gravitational wave detector, you would not notice. There is no flash, no sound, no sign, just a faint shiver in spacetime passing by. It is easy to imagine black holes pulling together with fury, but their union is not a crash, it is a slow, perfect convergence. Even at the end, they follow smooth curved paths until they merge. Often, black hole pairs form in busy places like globular clusters or during galaxy mergers. In such environments, stars and remnants bump into each other, and black holes can drift toward the center through dynamical friction. This is when a moving black hole stirs up stars behind it, making a wake that tugs it back, slowing it down and pulling it inward. Once two black holes are bound in a binary system, they are locked in a long relationship. They can sling nearby stars away in a process called a gravitational slingshot. This can shrink their orbit even before gravitational waves take over. In time, the waves become the main cause of orbital decay. Though they are weak, their effect adds up over millions of years, making the orbit smaller and faster until the last minutes, when it becomes a tight spiral from Earth. These final orbits make a rising chirp in the data as the waves grow stronger and faster. That chirp tells a story of motion, decay, and two giants closing in on one point in space. It is strange that the most powerful events in the universe begin so quietly, but that is how black holes work. They hum and draw together with perfect timing, carrying with them the memory of the stars they came from and the paths they traveled to meet. When two black holes finally come together, the moment is both the end of a long journey and the start of something new. For millions or billions of years they have circled each other, growing closer so slowly you could watch for a lifetime and never see a change. But in the final seconds everything speeds up, their orbits tighten, their speed rises until they are moving at a good part of light speed. Space-time itself twists and shakes as gravitational waves pour out. This is the loudest part of the event in gravitational terms. Even though there is no sound in space, detectors like LIGO and Virgo can hear the faint stretch and squeeze of these ripples as they pass through Earth. In those last few orbits the waves grow faster and stronger, making a chirp pattern in the data. Then, in less than a blink, the two black holes merge into one. The exact moment of merger is hidden from the outside world by the event horizon. We cannot see inside to watch it happen, but we can measure the energy it sends out. The new black hole is slightly lighter than the two combined, because some of the mass has turned into gravitational waves. In that brief instant, the energy released is more than all the stars in the observable universe give off in light. Yet it happens in total darkness. After the merger, the new black hole rings like a struck bell, sending out a final set of waves called the ringdown. These fade quickly, leaving a quiet, perfectly round black hole spinning in the dark. Its spin and size carry the history of its parents, telling scientists how big they were, how fast they moved, and how they met. These mergers are rare on human timescales, but across the universe they are common enough that detectors on Earth can catch several each year. Every detection adds to our picture of how black holes form, grow, and move. The discovery of gravitational waves in 2015 confirmed this, proving Einstein was right about their existence, and giving us a new way to explore the cosmos. Instead of just looking with telescopes, we can now listen to the vibrations of space itself. Each signal is like a postcard from a place we could never see, sent by objects we could never touch. black hole mergers also help us understand the population of black holes, their sizes, spins, and how often they find each other. Some mergers seem to come from black holes formed in star clusters. Others from galaxy collisions. In some cases, the merged black hole might get a kick from the uneven release of waves, sending it drifting away from its home, maybe even out of its galaxy. But no matter where they happen, these mergers are some of the most extreme events in nature. They turn the slow dance of gravity into a final, rapid step, folding space and time into new shapes, leaving behind a single silent survivor, invisible to the eye, but forever changing the shape of the universe around it. Black holes merging might seem like the end of their story, but in many ways, it is just another step in a larger cosmic cycle. After the collision, the new black hole is heavier, spinning faster, and ready to keep shaping its surroundings. If it is in a busy region, it can pull in gas, dust, and even stars, creating a disk of superheated matter that glows brightly in X-rays and other high-energy light. Sometimes the energy released can outshine entire galaxies. This is how we get quasars, the most luminous objects in the universe, powered by supermassive black holes feeding on huge amounts of material. While stellar mass black holes are small compared to these giants, their influence is still real. They can strip matter from a companion star in a binary system, creating jets and flashes we can detect from Earth. After a merger, the black hole's spin can be extreme, twisting spacetime around it in a process called frame dragging. Anything nearby has to swirl in the same direction as the spin. If it gets too close, the surrounding space is not calm. It can be full of debris from the event, heating up as it falls inward, yet over time things settle, and the black hole returns to quiet, waiting for its next encounter. Supermassive black holes at galaxy centers may grow through many such mergers, sometimes swallowing smaller black holes and stars like pebbles falling into a deep well. These events shape the galaxies themselves. The energy they release can blow away gas, stopping star formation, or stir up material, triggering new bursts of stars. Our own Milky Way has a supermassive black hole at its core, called Sagittarius A*, about 4 million times the mass of the Sun. It is quiet now, but in the past it may have been active, and in the future it could merge with the black hole in the Andromeda Galaxy when our galaxies collide billions of years from now. Such a merger would be slow, taking hundreds of millions of years from first approach to final union, all the while sending gravitational waves through the cosmos. Black holes are not isolated events. They are part of the living structure of the universe, born from stars, growing through feeding and merging, shaping galaxies, bending light, and marking the places where time and space fold in on themselves. Even after a merger, the story is not over, because the black hole remains, silent but present, a permanent reminder of the forces that shaped it, and somewhere, far away, another black hole may be moving closer, starting the same long, slow dance, ready to add another chapter to a story as old as the stars themselves. Black holes may seem far removed from our everyday lives, but the same physics that governs them shapes the world around us. Gravity holds our planet together, keeps the moon in orbit, and controls the motion of the solar system. The rules do not change just because a black hole is involved. It is the same gravity, only taken to the extreme. Studying black holes is not just about understanding exotic objects. It is about testing the limits of our theories. Every observation is a chance to see if Einstein's equations hold up under the most extreme conditions in nature. So far they have passed every test, but scientists keep looking for cracks. Maybe black holes will reveal where our understanding fails, leading to new physics. They are also a bridge between the two great theories of the 20th century, general relativity, which explains gravity on large scales, and quantum mechanics, which explains the smallest particles. At the singularity, these theories clash. We cannot yet describe what happens there. Finding that answer might require a theory of quantum gravity, something that unites the two. This is one of the biggest goals in modern science. Black holes are also connected to the beginning of the universe itself. Some theories suggest that right after the Big Bang, tiny black holes called primordial black holes could have formed, smaller than atoms but incredibly dense. If they exist, they could be a clue to the nature of dark matter, the invisible substance making up most of the mass in the universe. So far we have not confirmed them, but the search continues. In the meantime, the black holes we do know about keep teaching us. Gravitational wave detections are adding to a growing catalog. Each one is a new story of stars dying, collapsing, and coming together. Some show pairs with equal masses, others with one much bigger than the other. Some spins line up, others are tilted or even opposite. Each case helps us learn how black holes form and move. They are not all the same. Just as stars have many types, black holes have their own variety: stellar mass, intermediate mass, and supermassive, each with its own origins and role in the cosmos. Yet no matter the size, the defining feature is the same. Once you cross the event horizon, you are lost to the outside universe. Nothing escapes, not light, not matter, not even information in any form we understand. This last point raises one of the strangest puzzles in physics, called the information paradox. If nothing can escape a black hole, what happens to the information about what fell in? Does it vanish forever, breaking the rules of quantum mechanics, or does it survive somehow in a hidden form? Physicists have debated this for decades, with no final answer. Solving it might change our understanding of reality itself. Until then, black holes remain as much a mystery as a fact. They are real. We can measure them, see their effects, and even hear their mergers, but we cannot yet say we fully understand them. They sit at the edge of knowledge, pulling us toward deeper questions. One of the most fascinating parts of black hole science is the idea that they are not completely black. In the 1970s, physicist Stephen Hawking showed that black holes can emit tiny amounts of radiation, now called Hawking radiation. This happens because of quantum effects near the event horizon. Empty space is not truly empty. It constantly flickers with particle and antiparticle pairs appearing and disappearing. Normally they meet and vanish instantly, but near the event horizon, one particle can fall in while the other escapes. To an outside observer, it looks like the black hole is slowly losing energy over incredibly long timescales. This could make black holes shrink and eventually vanish. For a stellar mass black hole, this process is unimaginably slow, far longer than the current age of the universe. But for tiny black holes, if they exist, it could be faster. Hawking radiation links gravity, quantum mechanics, and thermodynamics, showing that black holes have a kind of temperature. This idea was shocking because it suggested black holes are not completely cut off from the rest of the universe. They can interact in subtle ways. It also connects to the information paradox. If black holes can evaporate, what happens to the information about what fell in? Does it come out in the radiation or is it gone forever? No one knows for sure. Solving this could lead to a deeper understanding of the laws of nature. Hawking's work also reminded scientists that black holes are not static. They can change over time, grow by feeding, merge with others, or shrink through radiation. They are part of the ongoing story of the cosmos, not frozen points. Our ability to study them has grown dramatically in recent years, from the first direct image of a black hole's shadow to the detection of dozens of gravitational wave events. Technology has opened a new window on these objects. Future space telescopes and improved detectors will let us see more details, maybe even catch black holes in the act of merging in real time. Space missions like LISA, the Laser Interferometer Space Antenna, will detect gravitational waves from supermassive black hole mergers, something current ground-based detectors cannot do. As we explore more, we may find answers to questions we have not even thought to ask yet. Black holes are both a challenge and an opportunity for science. They push our theories to the limit and force us to think in new ways. They are not just curiosities, they are central to understanding how the universe works, and as we learn more, they may turn out to be keys to some of the deepest mysteries in physics. Black holes might seem like the ultimate dead ends, but some scientists have wondered if they could also be gateways. Ideas like wormholes and white holes come from the same equations that describe black holes. A wormhole would be a tunnel through spacetime, connecting two distant points or even different universes. A white hole would be the opposite of a black hole, a place where nothing can enter and matter only comes out. These ideas are mostly theoretical and have no direct evidence, but they are fun to explore because they push our imagination to the limits of physics. In theory, a black hole could connect to another place through a wormhole, but in practice, such a tunnel would likely be unstable and collapse before anything could pass through. Still, The math leaves room for possibilities, and science fiction has used them for decades, while wormholes may not be real. Black holes do shape spacetime in ways that can send matter and energy on strange paths, jets of particles from around feeding black holes can travel thousands of light years, lighting up the space between galaxies. These jets are not coming from inside the event horizon but from the hot disk of matter swirling around it. Magnetic fields twist and focus the particles, sending them outward at near light speed. Such jets can affect galaxy growth, heating gas and stopping it from forming stars, or triggering star formation in other regions. Black holes are not just consumers, they are also influencers. In the cosmic ecosystem, they regulate the flow of matter and energy on huge scales. In this way, they are connected to everything from the birth of stars to the shape of galaxies, and maybe even the conditions for life. Without them, the universe might look very different. The mystery and the influence of black holes make them one of the most important topics in astrophysics. They are simple in some ways, defined by just mass, spin, and charge, yet the effects of those three numbers can be as complex as the universe itself. They sit in the quiet centers of galaxies or drift invisibly between the stars, shaping the cosmos without a sound, and while we may never see inside one, studying their edges has already changed how we think about space, time, and the nature of reality. They remind us that the universe is not just a collection of objects but a network of relationships, forces, and possibilities that stretch beyond our senses, and that somewhere out there, beyond the reach of light, something is bending the rules in ways we are only beginning to understand. In the end, black holes are not just about destruction, they are part of a grand cosmic balance. Stars live, shine, and die, and in their most extreme deaths, they leave behind these silent markers of gravity's ultimate power. They are reminders that nothing lasts forever, but also that endings can lead to new beginnings. The heavy elements forged in the death of massive stars are scattered into space, becoming the building blocks for planets, oceans, and life. Without that cycle, we would not be here. Black holes also teach us humility. They show us that the universe is bigger, stranger, and more complex than our daily lives suggest. They force us to accept that there are places we cannot go and things we cannot see, yet even from a distance, we can understand them through science. The fact that we can detect the ripples from two black holes colliding billions of light-years away is a testament to human curiosity and ingenuity. It means we can reach across space and time with nothing but thought, math, and technology, and bring back stories from places we will never touch. Black holes may keep their secrets, but they have already given us so much. They have confirmed Einstein's theories, opened the era of gravitational wave astronomy, and inspired countless people to look up and wonder. They will continue to challenge us, to push our understanding, and to remind us that the universe is not static but alive with motion and change. In their darkness, there is light. For the mind, in their silence, there is a story for the imagination, and as long as we keep listening, they will keep speaking in the language of gravity, quietly shaping the future of the cosmos. Somewhere, right now, a star is burning through its last fuel, on its way to becoming a black hole. Somewhere else, two black holes are spiraling toward each other, their final dance already sending ripples across space, and far away. Perhaps a black hole is slowly evaporating, a whisper of radiation, marking the slow passage of unimaginable time. All of it is part of the same vast, connected story, one we are lucky to witness from our small blue world. So when we think about black holes, we should not just see them as cosmic monsters swallowing everything, but as natural results of the universe's own rules. They are not mistakes or accidents, they are what happens when gravity, mass, and time push each other to their limits. They are proof that the universe is dynamic, always changing, always testing the boundaries of what is possible. From the smallest stellar mass black holes left behind by dying stars to the supermassive giants anchoring galaxies, they are part of the structure of everything. We may never stand on their edge or look inside, but we can map their effects, predict their behavior, and listen to their mergers. With each discovery, they move from mystery to understanding. Though never fully losing their sense of wonder, they remind us that even in a universe governed by clear laws, there is still room for the unknown, for the surprising, and for the beautiful. In their darkness, they hold not just the matter of stars, but the questions that drive science forward. What happens at the singularity? Can information ever truly be lost? Do they connect to other places in spacetime? Are they the key to uniting gravity and quantum physics? These are not just technical puzzles. They are questions about the nature of reality itself. The search for answers may take centuries, and we may never have them all. But in looking, we learn more about ourselves, about our place in the cosmos, and about the delicate balance of forces that makes existence possible. Black holes are both the end of a star's story and the beginning of new ones. They are timeless in ways we can barely imagine, yet they shape the very flow of time around them. And somewhere out there, beyond the reach of our senses, more are forming even now, silent, invisible, and waiting for us to find them. They are the universe's most extreme expression of gravity, and in studying them, we are really studying the edges of the possible, a journey with no final horizon. The story of black holes is also the story of human curiosity. For most of history, the idea that something could have gravity so strong that light itself could not escape was just a strange thought experiment. In the late 1700s, an English scientist named Jean Michel and a French scientist named Pierre-Simon Laplace both suggested the idea of dark stars, objects so massive and compact that light could not get away. At the time, light was thought to be made of tiny particles, so the idea fit the science of the day. But it was forgotten for more than a century. When Einstein published his theory of general relativity in 1915, the equations made it possible to describe such objects in a new way. Only a year later, Karl Schwarzschild, working as a soldier in World War I, solved Einstein's equations for the case of a perfectly spherical mass. His solution described what we now call the Schwarzschild radius, the point where the escape speed equals the speed of light. It was a mathematical curiosity, but few believed such objects could exist in reality. Over the decades, more scientists explored the idea, and by the mid-20th century, with the discovery of neutron stars, the possibility of black holes became harder to ignore. They moved from strange theory to real astrophysical objects. In the 1960s, physicist John Wheeler gave them the name black holes, and the term stuck. The first candidates were found not by seeing the black holes themselves but by detecting their effects on nearby matter. Bright X-ray sources like Cygnus X revealed the presence of invisible massive objects pulling material from companion stars. From there, the search grew, and each discovery made black holes feel less like science fiction and more like part of the normal universe. Yet the more we found, the more questions we had, and the deeper the mystery became. Black holes had gone from an odd equation to one of the most important subjects in astronomy, showing us how theory, observation, and imagination work together to uncover the universe's secrets. The search for black holes has been powered by some of the most advanced telescopes and space missions ever built. On Earth, huge radio dishes and X-ray observatories scan the skies for signals that reveal matter heating up as it falls toward a black hole. In space, satellites like Chandra X-ray Observatory, SWIFT, and NuSTAR give us a clear view of high-energy light that cannot reach the ground because our atmosphere blocks it. In 2019, the Event Horizon Telescope, a network of radio telescopes around the world working together, captured the first image of a black hole's shadow in the galaxy M87. This image showed a glowing ring of gas heated to extreme temperatures as it spirals in, with the dark center marking the event horizon. It was a scientific and cultural milestone, proving that we could see the unseeable. Future missions aim to go even further. The James Webb Space Telescope can peer into dusty galaxy centers to study the environment around supermassive black holes. The upcoming LISA mission will float in space to detect gravitational waves from black holes far larger than the ones LIGO and Virgo can hear. Combining these tools lets scientists explore black holes across all sizes and distances, from small stellar mass holes just a few times the Sun's mass to monsters with billions of solar masses. Each telescope, each mission, adds a piece to the puzzle, showing us that black holes are not rare, but common features of galaxies. By using every wavelength of light and even ripples in spacetime, we are building a complete picture of how they form, grow, and shape the cosmos. This global effort shows that the story of black holes is not just about the objects themselves, but also about the human drive to understand, a drive that crosses borders, languages, and generations. turning the dark heart of the universe into a shared source of wonder. Black holes may all follow the same basic rules of gravity and spacetime, but they come in different sizes, origins, and environments, each with its own story to tell. The smallest ones we know are called stellar mass black holes, formed when massive stars collapse at the end of their lives. These usually have between about 3 and a few dozen times the mass of the Sun. They are scattered across galaxies, often hidden, sometimes found in binary systems where they feed on a companion star. Cygnus X-1 is one of the most famous examples. Discovered in the 1960s, it was the first strong black hole candidate, located about 6,000 light-years from Earth in the constellation Cygnus. It pulls gas from a massive blue star, heating it until it glows brightly in X-rays. Then there are intermediate mass black holes, a mysterious middle category with hundreds to thousands of solar masses. They are harder to find because they are too big to form from a single star and too small to sit at the centers of galaxies like supermassive ones. Some may form from repeated mergers of smaller black holes or from the collapse of giant star clusters. A possible example is HLX-1, found in a galaxy called ESO 243-49, which may be a stripped-down core of a small galaxy that merged with a bigger one. The largest black holes are supermassive black holes, with millions to billions of times the mass of the Sun. These monsters sit at the centers of most galaxies, including our own Milky Way, our central black hole, Sagittarius A*, has about 4 million solar masses and was discovered through decades of observing stars orbiting an invisible point. These orbits were measured with extreme precision, showing that only something incredibly dense could hold them in place. Other supermassive black holes are even more extreme. The one in M87, famously imaged by the Event Horizon Telescope, is about 6.5 billion times the mass of the Sun. Its event horizon is bigger than our entire solar system. The biggest known black holes, like TON 618, may reach tens of billions of solar masses, swallowing matter at a rate that produces blinding quasars visible across the universe. Each category of black hole plays a role in cosmic evolution. Stellar mass ones recycle matter from dying stars. Intermediate ones may link star clusters to galaxy growth. And supermassive ones help shape the structure of galaxies themselves. Scientists also suspect there could be a fourth category, primordial black holes. Tiny but possibly numerous, formed in the chaos after the Big Bang. If they exist, they could be as small as an atom but with the mass of a mountain. They might even make up dark matter, though we have no direct proof. The variety in size and origin shows that black holes are not one size fits all. They are part of a spectrum, born in fire, grown in mergers, or seeded in the earliest moments of time. Studying each type is like looking at a different chapter of the universe's biography. The smallest tell us about the lives and deaths of stars, the middle-sized hint at hidden structures and rare processes, and the largest reveal the deep connection between gravity, light, and the architecture of the cosmos. They are all bound by the same basic truth. Cross the event horizon, and you are gone from the visible universe, no matter if it is a few kilometers across or billions of kilometers wide. In every case, a black hole is a place where matter and energy are pushed beyond the limits of space and time, and knowing their types is not just a classification, it is a way to understand the different paths the universe takes to create these cosmic extremes, from the death of a star to the heart of a galaxy, from the tiniest ripple in spacetime to the largest structures we know. Black holes of all kinds are connected by the same invisible thread of gravity, shaping everything from the fate of individual stars to the flow of entire galaxies. If black holes are the ultimate test of gravity, then they are also the perfect stage for exploring the wildest possibilities in physics. One of the most mind-bending ideas is time travel, not in the science fiction sense of hopping into a machine and appearing in the past, but in the real physics sense of how time can slow down or stretch near extreme gravity. This is called time dilation. And it is not just theory. It has been measured with satellites, atomic clocks, and even in the way GPS systems work. The closer you are to a massive object, the slower time passes for you compared to someone farther away. Near a black hole, this effect is so strong it could let you experience hours while years pass for someone else. In the movie Interstellar, this idea was shown when the crew landed on a planet near a supermassive black hole and found that every hour there was equal to 7 years outside. While Hollywood exaggerated some parts, the core concept came straight from Einstein's equations. The bending of spacetime near the event horizon makes time flow at different rates. It is a one-way trip into the future for anyone who ventures close, but the black hole's influence on time is just the start of the strange possibilities. Some scientists have speculated about wormholes, tunnels through spacetime that could link distant parts of the universe. The math of general relativity allows them in theory, and some solutions even connect them to black holes. In this picture, a black hole could be an entrance to a wormhole, with a white hole, the reverse of a black hole, at the other end, spewing matter and energy instead of trapping it. The problem is stability. Any matter or light entering would likely make the wormhole collapse instantly, so the idea remains speculative. Still, the possibility inspires both physicists and storytellers because it suggests that black holes might not just be dead ends, they could be shortcuts, gateways, or windows into other universes. Another mind-twisting concept is the holographic principle, which suggests that all the information about what falls into a black hole might be stored on its surface area, like a cosmic hard drive. This could solve the information paradox and connect gravity to quantum physics in a new way. If true, it would mean that the three-dimensional space inside the black hole is just a kind of projection. Much like a hologram on a flat surface, these ideas are not proven, but they push us to think beyond the limits of ordinary experience, to imagine the universe as a place where time can stretch, space can fold, and reality itself can have hidden layers. Black holes are the laboratories where these extreme ideas can be tested, not with hands-on experiments, but with careful observation, precise measurement, and the most powerful tools of human thought. They are like the edge of a map marked, "Here be dragons." A place that draws explorers because it is both dangerous and full of potential. By studying them, we are not just learning about gravity, we are asking whether the universe has shortcuts, secrets, and surprises waiting beyond the horizon, and in doing so, we are learning how to think about possibilities far beyond our small world. Black holes are not only a playground for theoretical physics but also a central force in shaping the actual structure of the universe. Without them, galaxies might look and behave completely differently. At the hearts of most large galaxies, supermassive black holes act like engines, controlling the flow of matter and energy on scales far beyond their size. When they feed on gas and dust, the material forms an accretion disk, heating to millions of degrees and creating powerful outflows. These outflows can blast through the galaxy, pushing gas away and shutting down star formation, or in some cases, compressing gas and triggering bursts of new stars. This feedback cycle is one reason galaxies stop forming stars after a certain point in their lives. In the early universe, young supermassive black holes powered quasars, which are among the brightest objects we can see. Some of these quasars are so far away that their light has taken more than 12 billion years to reach us, meaning we are seeing them as they were when the universe was less than a tenth of its current age. The energy from these early black holes likely played a role in reionizing the universe, a phase when the first stars and galaxies lit up and transformed the cosmic environment. Black holes also shape galaxy clusters, the largest structures held together by gravity. In the cores of these clusters, supermassive black holes send jets of high-energy particles into the surrounding hot gas, preventing it from cooling and forming stars too quickly. These jets can stretch hundreds of thousands of light years, like cosmic fire hoses, influencing regions far beyond the black hole's immediate neighborhood. Even smaller black holes can have dramatic effects on their surroundings. In binary systems, they can strip material from a companion star, creating X-ray binaries that flash and flicker as the flow of matter changes. In some rare cases, black holes can even be part of triple systems, where gravitational interactions can cause sudden changes in their orbits, leading to mergers faster than they would otherwise happen. The influence of black holes is not limited to shaping matter. They also bend light in ways that let us see deeper into space. This is called gravitational lensing. When light from a distant object passes near a massive body like a black hole, its path is curved, creating arcs, rings, or multiple images of the same source. Gravitational lensing has become a powerful tool in astronomy, helping scientists detect galaxies too faint to see directly and even find planets around other stars. In rare cases, if a black hole passes in front of a background star, it can cause the star to brighten temporarily, an event called microlensing, giving away the black hole's presence. All these effects show that black holes are not isolated, silent objects. They are active participants in the cosmic ecosystem, sculpting galaxies, influencing star birth, stirring gas, and bending light. They are part of the invisible framework that holds the visible universe together, and studying their influence tells us as much about the grand structure of the cosmos as it does about the black holes themselves. In this way, they are both destroyers and creators, both limiters and enablers, both edges and centers in the great design of everything. Black holes have not only changed the way scientists think about the universe, they have also deeply influenced culture, art, and the human imagination. Long before we had any proof they existed, writers, poets, and filmmakers were fascinated by the idea of a bottomless cosmic pit or a doorway to the unknown. In the 19th and early 20th centuries, early science fiction authors like H.G. Wells and Olaf Stapledon wrote about strange cosmic phenomena that hinted at similar concepts. By the mid-20th century, as astronomy advanced, black holes began appearing in pulp magazines, comic books, and eventually blockbuster movies. In science fiction, black holes have been portrayed as portals to other universes, weapons of unimaginable power, or places where reality itself folds in ways that defy logic. In Star Trek, black holes sometimes act as shortcuts across space, while in Doctor Who, they are woven into plots involving time travel and cosmic danger, one of the most famous modern depictions is the 2014 movie Interstellar, which consulted real astrophysicists to create Gargantua, a scientifically accurate spinning black hole whose gravity bent light into a glowing halo. The visual effects were so realistic that they ended up being used in academic papers. Other films like Event Horizon used black holes as horror elements, imagining them as gateways to terrifying dimensions. Beyond cinema, black holes are symbols in music, art, and literature. Pink Floyd's The Dark Side of the Moon album and Muse's Supermassive Black Hole song both use them as metaphors for emotional or psychological states. Artists have painted abstract swirls and voids to capture the idea of something that consumes without return. In everyday language, the term black hole has escaped science entirely. People talk about falling into a black hole when describing depression, financial collapse, or the endless distraction of the internet. The metaphor works because it captures both the sense of inescapable pull and the loss of something into an unknown place. In modern art, black holes often symbolize both destruction and transformation, an erasure of what was and the birth of something new. Educators and outreach programs also use black holes as a gateway to inspire interest in space. Their mystery draws in students who might not otherwise be curious about science, and once they are hooked, teachers can use black holes to explain deep concepts like relativity, quantum mechanics, and the life cycles of stars. NASA, ESA, and other space agencies often release striking images and animations of black holes to capture public imagination. Social media spreads these visuals quickly, making black holes part of the global conversation. The Event Horizon Telescope image of M87's black hole in 2019 became a cultural moment, trending worldwide and even being turned into memes, showing how science and culture can intersect in unexpected ways. In this way, black holes act as a bridge between scientific discovery and creative expression. We study them with telescopes and equations, but we also dream about them, fear them, and turn them into stories. They are both hard data and pure symbol, and that dual nature is rare in science. Perhaps this is why they will always remain at the center of human curiosity, because even as we uncover more facts, the unknown heart of a black hole still invites imagination, and it is that blend of truth and mystery that keeps people looking up at the night sky, wondering not just what is out there, but what it means for us. If the past century has been about discovering and proving that black holes exist, the next century may be about exploring them in ways we once thought impossible. Future research into black holes is poised to push both technology and human imagination to new heights. The Event Horizon Telescope will continue to improve, adding more radio observatories to sharpen its vision and allow for real-time movies of matter swirling into a black hole. Scientists hope to capture the dynamic changes in the glowing ring around the event horizon, watching gas clouds fall in and jets blast out. Space-based missions like LISA, the Laser Interferometer Space Antenna, will detect gravitational waves from mergers of supermassive black holes billions of light-years away, something ground-based detectors cannot pick up due to their size limits. By measuring these low-frequency waves, LISA will give us a view of the slow, colossal dances of galactic giants as they spiral together. Other proposals like the Black Hole Explorer mission aim to place telescopes in orbit around Earth or even farther out to create sharper, interference-based images of black holes. We may one day be able to map the twisted spacetime around them with incredible precision. Another frontier is multi-messenger astronomy, combining gravitational waves, light, neutrinos, and even cosmic rays to get a complete picture of black hole events. For example, when a neutron star and black hole merge, we might detect the gravitational waves from the collision, the flash of gamma rays from the ejected matter, and the chemical fingerprints in the debris, all telling different parts of the same story. These methods will also help answer big questions about black hole growth, like how the earliest supermassive black holes in the universe formed so quickly. Some must have reached millions of solar masses when the universe was only a few 100 million years old, which challenges our current understanding of galaxy evolution. Answering this might require new theories or entirely new physics. There is also the hope of directly testing what happens at the event horizon, Using precise measurements of light bending and timing, scientists could confirm whether it matches predictions from Einstein's relativity or if tiny deviations hint at quantum effects. On the more speculative side, some researchers dream of sending probes close to black holes, not to enter them, but to orbit just outside and study their environment up close. Such missions are far beyond our current technology, but not beyond imagination. Like the early dreams of space travel, they could one day become real if humanity develops faster propulsion, stronger radiation shielding, and advanced AI capable of piloting in extreme conditions. The data from such a mission could transform physics, giving us direct evidence of phenomena we now only model in simulations. The study of Hawking radiation is another future focus, while we cannot detect it. From large black holes, some theories suggest that tiny black holes, if found or created, could produce measurable amounts. Experiments with high-energy particle collisions have searched for micro-black holes that might briefly appear and evaporate, so far without success. But even the search itself teaches us more about the limits of our theories. In all these ways, the next century of black hole science is not just about confirming what we already believe. It is about looking for the cracks in our understanding, the anomalies that force us to rewrite the rules. Black holes may hold the key to uniting the physics of the very large and the very small, and while that goal may take decades or centuries, every step toward it will reveal something new about the nature of reality. The journey ahead is as vast as the universe itself, and the horizon is only the beginning. Black holes are often described as the most extreme objects in the universe, but they are also among the most unifying, connecting different fields of science in ways few other topics can. Studying them requires astrophysics to understand their formation and growth, general relativity to describe their effect on spacetime, quantum mechanics to explore their possible evaporation, computer science to simulate their behavior, and engineering to design the instruments that can observe them. This makes black holes a crossroads where multiple disciplines meet, each bringing its own tools and questions. The history of black hole research is full of examples where progress in one area sparked advances in another. The detection of gravitational waves from black hole mergers was only possible because of decades of innovation in laser technology, vibration isolation, and data analysis algorithms. The Event Horizon Telescope's image was only possible because of advances in network synchronization, atomic clock accuracy, and massive data storage. In this way, black holes are catalysts for technological progress, pushing us to solve problems that end up benefiting other fields, even beyond science. Black holes connect to philosophy. They challenge our ideas about time, space, and what it means for something to exist. They raise questions about determinism and free will, about whether information can ever be truly lost, and about the nature of reality itself. Some philosophers have compared black holes to thought experiments in metaphysics, places where the rules we take for granted are tested to the breaking point. They also connect to the human experience in a symbolic way. People see them as metaphors for deep change, for situations where something is lost forever, or for the unknown parts of life we must face without complete understanding. In literature and art, this symbolism has taken countless forms, from the black hole as a symbol of grief to the black hole as a metaphor for hidden potential. In education, black holes offer a unique chance to connect abstract ideas to something concrete. A teacher explaining curved spacetime might struggle to make it real until they bring up a black hole. Suddenly, the concept becomes visual, tangible, and exciting. In this way, black holes serve as ambassadors for science, drawing people in with mystery and keeping them engaged with wonder. They are also unifying in the sense that they belong to everyone. No one country or culture owns the black holes in the sky. The search for them has been a truly global effort, with observatories, scientists, and students from every continent contributing. In a world often divided, the study of black holes is one of those rare areas where humanity works together toward a shared goal. This shared curiosity is perhaps one of the most important things they give us. A reminder that while the universe may be vast and cold, our drive to understand it is a warm and common thread. In the end, black holes are more than just objects. They are stories, challenges, symbols, and bridges. They link the smallest quantum scales to the largest cosmic structures. They turn math into images, theory into discovery, and curiosity into collaboration. As long as they exist, and as long as we exist, they will continue to pull us toward them, not just with gravity, but with the irresistible force of questions we cannot yet answer, and perhaps that is their greatest gift, to remind us that there will always be more to learn, more to explore, and more to wonder about beyond the horizon. The study of black holes also forces us to confront the limits of our current scientific theories. General relativity has been tested countless times and remains our best description of gravity on large scales, but when applied to the very center of a black hole, at the singularity, the equations break down. They predict infinite density and zero volume, a state that makes no physical sense. This is not just a math problem, it is a sign that our understanding is incomplete. To truly know what happens inside a black hole, we need a theory that unites general relativity with quantum mechanics. This elusive goal is called quantum gravity, and black holes may be the perfect testing ground for it. Some approaches, like string theory, suggest that what we think of as a singularity might be replaced by a dense, stringy core, while others propose that the inside of a black hole could be a vast region of spacetime connected to somewhere else. There are even loop quantum gravity models that suggest space and time themselves are quantized, meaning they are made of tiny indivisible units, and that the singularity is replaced by a bounce, possibly leading to the birth of a new universe. These are bold ideas, but they show how black holes push scientists to go beyond the boundaries of established physics. Another frontier is the information paradox, famously posed by Stephen Hawking. If black holes truly erase all details of what falls into them except mass, charge, and spin, then information is lost forever, but this violates a fundamental rule of quantum mechanics, which says that information cannot be destroyed. Solving this paradox has led to theories like the holographic principle, which suggests that the information is somehow preserved on the event horizon itself, encoded in 2 dimensions, like a cosmic film reel. Resolving this issue is not just about black holes. It is about the foundations of physics, because whatever solution we find will likely apply to all quantum systems in curved spacetime. This is why black holes are sometimes called thought experiments of the cosmos. They are nature's way of showing us where our understanding breaks, and where we need new ideas. Yet what makes them especially fascinating is that we can actually observe their effects in the real universe. Unlike purely abstract concepts, black holes give us data, through X-ray emissions, gravitational waves, and the motion of nearby stars, that can confirm or challenge our models. The fact that something so exotic can be studied with real instruments is a rare gift in science. It is a reminder that even the most extreme, mind-bending phenomena are still part of the same reality we live in, governed by the same fundamental rules, waiting to be understood. Black holes also inspire one of the most daring ideas in space exploration, the possibility of using their immense gravitational power for travel. While falling into a black hole would be fatal, approaching one carefully might allow for something called gravitational slingshotting. This technique is already used in our solar system, where spacecraft like Voyager and New Horizons gain speed by passing near planets. But around a black hole, the effect could be far greater. A close pass, executed with perfect precision, could accelerate a spacecraft to an incredible fraction of the speed of light, reducing travel times across interstellar distances. In theory, if humanity ever develops ships capable of surviving extreme tidal forces and radiation, black holes could become interstellar waypoints, not destinations, but speed boosters. Another possibility is extracting energy from a rotating black hole, a concept first proposed by Roger Penrose, called the Penrose process. By sending matter into the ergosphere, the region outside the event horizon where space itself is dragged around, it may be possible to split particles so that some escape with more energy than they entered, essentially stealing rotational energy from the black hole. Scientists have also imagined using the Hawking radiation from small artificial black holes as an energy source. In this vision, a civilization could create a micro-black hole, keep it stable, and capture its steady output of energy for power. This is far beyond our current technology, but it is a fascinating intersection of astrophysics and engineering. These ideas link black holes to the concept of the Kardashev scale, which measures a civilization's technological level by the amount of energy it can use. A civilization capable of manipulating black holes for energy or travel would be far beyond a Type II, stellar harnessing, society. Perhaps approaching Type III, which uses the energy of an entire galaxy. This speculation also fuels the search for extraterrestrial intelligence. Some researchers have suggested that advanced alien civilizations might leave detectable signs if they were using black holes in these ways: unusual radiation patterns, stable orbits around otherwise invisible points, or even gravitational wave signals could hint at artificial activity. While these possibilities are purely hypothetical today, they show that black holes are not only objects of study but also potential tools, gateways, and markers of advanced life. In science, such speculation is valuable, because it forces us to think creatively about what is possible, not just what is likely. Even if we never reach the level where we can approach a black hole safely, the very act of imagining it pushes our understanding of physics, engineering, and the limits of human potential. And in that sense, black holes are not just end points in space. They are starting points for new dreams. The story of black holes is still being written, and perhaps the most exciting thing about them is that we do not yet know how many surprises they still hold. Every major discovery about black holes in the last century was something no one predicted when the idea was first proposed. Early astronomers never imagined we would detect their mergers through ripples in spacetime, or that we could capture an actual image of one's shadow from millions of light-years away. This pattern suggests that the future will bring equally unexpected breakthroughs. One area ripe for discovery is the population of intermediate-mass black holes, objects that are heavier than stellar black holes but lighter than the supermassive giants at galaxy centers. Finding and studying these missing link black holes could reveal how the biggest ones grew in the early universe. Another frontier is mapping black holes in our own galaxy with unprecedented accuracy. Future telescopes could detect thousands more, revealing hidden patterns in their distribution and connections to the Milky Way's history. There is also growing interest in primordial black holes, hypothetical objects formed in the first fraction of a second after the Big Bang. If they exist, they could range from tiny subatomic sizes to masses of thousands of suns, and they might even explain part of the mysterious dark matter. Detecting one would revolutionize both cosmology and particle physics. On the theoretical side, the quest to merge general relativity and quantum mechanics continues. Experiments in gravitational wave astronomy may one day reveal subtle differences from Einstein's predictions, pointing the way to a deeper theory of spacetime. And while the idea of using or visiting black holes remains far in the future, every improvement in propulsion, materials, and robotics brings us closer to the kinds of missions that once seemed pure fantasy. Black holes also serve as a constant reminder of our place in the cosmos. They are among the oldest and most enduring structures in the universe, and long after the last stars fade, they may remain, slowly evaporating over unimaginable spans of time, yet for all their darkness, they have become beacons for human curiosity, drawing together scientists, engineers, artists, and dreamers from every culture. Perhaps their greatest lesson is that even the most extreme unknowns can be approached with patience, creativity, and collaboration. The horizon may mark a boundary beyond which we cannot see, but it also marks a challenge, an invitation to keep exploring, and to believe that the universe will always have more to show us, as long as we are willing to look.